Hello, welcome to another episode of Physics is Easy with Mr. Jesse. This tutorial aims to solve a problem on calorimetry and phase change. This is one of the problems I have given in WebAssign. It reads 108 grams cube of ice at 0 degrees Celsius is dropped into 1 kilogram of water that was originally at 85 degrees Celsius. What is the final temperature of water after the ice has melted? So since this problem involves two substances at different temperatures, and then eventually they're going to reach thermal equilibrium, the appropriate equation that we're going to use here would be Q gained is equal to negative Q lost. And in this case, what would lose heat is the water that was originally at 85 degrees Celsius, because it is the substance that is much hotter, and the energy that is being lost by water is the one that is gained by ice. This heat gained by ice would cause the ice to do the following things. First is that because of the heat that it gained from water, the ice will melt. The ice will melt to water at 0 degrees Celsius. 0 degrees Celsius. After that, this heat again that is gained by ice would cause the water at 0 degrees Celsius to increase its temperature. So water at 0 degrees Celsius increases its temperature. Increases its temperature. And now since the water since the water at 85 degrees Celsius loses heat, a direct effect for that for the water at 85 degrees Celsius would be to lower its temperature. So say water at 85 degrees Celsius cools down. Then we could set up our equation or expand our equation, which is Q gained is equal to negative Q lost. So for Q gained, we will have two parts. The first part would be MLF, or the mass of ice multiplied by the latent heat of fusion of water. So again, that would be M of ice multiplied by the latent heat of fusion of water or ice, because in fact latent heat of fusion is actually very specific for a particular substance. So we have M ice multiplied by latent heat of fusion, plus, since this ice now will become water as it melts, then we would say M of water. Again, this water comes from ice that has melted, multiplied by the specific heat capacity of water, multiplied by the change in temperature, is equal to negative Q loss. So in this case, it would be the mass of water, and we're talking about the water which is at 85 degrees Celsius, multiplied by the specific heat capacity of water, multiplied by the change in temperature. And now let us substitute our value. So the mass of ice is 108 grams. We need to convert that into kilograms. So that would be 0.108 kilograms multiplied by the latent heat of fusion of water, that is equal to 3.33 times 10 to the negative 5. This is a certain constant, and most likely it will be given in a table, plus the mass of water. So basically this mass of water here is the same as the mass of ice, because it is just the melted ice to begin with. So that would just be 0.108 kilograms multiplied by the specific heat capacity of water. Now take note, we are not using the specific heat capacity of ice, because again the ice has already melted and it became water. and that is equal to 4186 multiplied by the change in temperature. So we need to solve for the final temperature. In fact, this is something that we don't know. What is the final temperature of the water after the ice has melted? Minus the initial temperature of water, so that's 0 degrees Celsius. Again, this is just the ice melting, is equal to negative. We have the mass of the water at 85 degrees Celsius, and that's 1 kilogram, multiplied by the specific heat capacity of water, which is 4186, multiplied by the change in temperature, which is TF, from a final temperature, minus the initial temperature of water, which is 85 degrees Celsius. Manipulating this equation would allow us to solve for TF, and TF is approximately equal to 69 degrees Celsius. For problems involving thermal equilibrium, it is very important to note that your final temperatures should fall within the range of the temperature of the cold substance and the temperature of the hot substance. So in this case, our expected final temperature should be between 0 degrees Celsius and 85 degrees Celsius. So as a matter of fact, 69 degrees Celsius is very much acceptable. And therefore, we have solved our problem. And that concludes this tutorial. Once again, always remember, physics is easy with Mr. Jesse.